In this problem, we're defining the current I1 using nodal analysis. We can see where I1 is labeled on the diagram. We're going to use nodal analysis, so we're going to use our problem-solving strategy entitled AC Steady State Analysis, as well as the one entitled Nodal Analysis. And if we look back at our problem-solving strategy for nodal analysis, we'll see the first step is determining the number of nodes in the circuit. And so if we look at our circuit, for instance, we have a node here, have one at the bottom, we have one here, we have one here. Now we could say we have one here, but I'm going to combine these two impedances in series for one impedance. So really, we have 1, 2, 3, 4, 5 nodes. Okay. So we have 5 nodes, and that means we're going to have 4 node voltages because we're going to pick one as the reference. So let's pick the bottom node as a reference node, and we'll go in and I'm going to name or label this node voltage V1, this node voltage V2, this node voltage V3, and this node voltage V4. Okay. So we have 5 nodes, so we have 4 node voltages because we're going to select one of them as the reference node. Now, if we look, we have 4 node voltages. That means we're going to need 4 equations. Okay. Now, we have a couple of voltage sources connected between the node and the reference, so we're going to have 2 constraint equations. One of those constraint equations is V3 is equal to 12 at an angle of 0 degrees, and the other one is V4 equal to 6 at an angle of 0. Okay. So that means that we need 2 more equations in terms of V1 and V2 and those little node voltages to be able to solve. Okay, so let's keep in mind those equations. Now if we look at our circuit, again, let's remember, here's a reference node, here's V1, here's V2, V3, and V4. And remember, we need 2 equations, okay, because we have 2 constraint equations. And the way we're going to get those is we're going to apply KCL at those 2 nodes. We're not going to apply KCL at the nodes where we have voltage sources. So, at this node, okay, we'll have V1 minus 12 at an angle of 0 divided by 3 plus J2. Okay, that's the current flowing through this way. Then the current flowing down through the J3 is V1 minus 6 at an angle of 0 divided by J3. And then we'll have a current leaving over in this direction. So that's V1 minus V2 over 4 equal to 0. Now if you simplify that simplifies into V1 times 0.4808 minus J 0.4872 minus 0.25 V2 equal to 2.7692 minus J 3.8462. Okay, so there's our first equation. Now for our second equation, we're going to apply KCL at this node. And if we look, for instance, we have a current leaving down through the minus J2. So we have V2 over minus J2. Then we'll have another current leaving the node in this direction. So we have V2 minus V1 over 4 equal to 3. at an angle of 10 degrees. That's the current entering from that source. So if we simplify, we'll have minus 0.25 V1 plus 0.25 plus J 0.5 V2 equal to 2.9544 plus J 0.5209. And that's our second equation. So now, if we solve those two equations, notice those two equations are in terms of V1 and V2. So solving using MATLAB, we get V1 is 10.5 at an angle of minus 12.12 degrees. V2 is 9.88 at an angle of minus 63.75. Now if we look at our circuit, we can note, for instance, if we look at I1 here, that I1 is going to be V1 minus 12 at an angle of 0 divided by 3 plus J2. So then I1, which is V1 minus 12 at an angle of 0 divided by 3 plus J2, so we have 10.5 at an angle of minus 12.12 minus 12 at an angle of 0 over 3 plus J2. That gives us I1 is 0.7781 at an angle of minus 161.9 degrees.